Good morning. It is 1:03 Eastern time. So good morning to everyone that's East Coast and farther west. And I guess good afternoon to everyone that's farther east. My name is Bill McShane. I work for the Department of Energy's Water Power Technology Office. I'm really pleased to be part of this presentation today, or just kicking it off and letting the rest of the team run with it. We're here to discuss innovation methods, methods helping us solve our most challenging problems and contradictions. And this is the first, this is another meeting in support of our prize participants in phase 2 of the InDEEP Prize. Next slide, please. And just some quick webinar logistics. Everyone, the participants should be in listen only mode. There may be a way to take you guys off when we do Q&As at the end. Audio issues, if you're having trouble with your audio over the internet, there should be a way that you can switch to audio over your phone, so try that. If that doesn't work, there's also the Zoom Help Center webpage. And as we definitely want to solicit your questions, your feedback, so definitely put your questions into the Q&A at the bottom of the Zoom toolbar, and we'll be answering as many questions as we can at the end of the meeting. And with that, thanks again for everyone's attendance, and I'll hand it off to Nicole Mendoza. Thanks.
Great, thanks everyone. So as Bill graciously mentioned, this webinar is part of a series of webinars supporting the Innovating Distributed Embedded Energy Prize. The prize has a $2.3 million prize pool spread across 3 phases over 2 years. We are currently accepting applications for phase 2, and the goal of the InDEEP Prize is to incentivize progress in early stage research, particularly in the technology domain of distributed embedded energy converters. For more on that, please see the recording from last week. And another goal of the prize is to help solve technical challenges that could be applied from outside wave energy to wave energy. Next slide, please. So participation and attendance at this webinar contributes to your score, kind of like extra credit or bonus points when the phase 2 applications are scored. Please follow these instructions here to make sure that you get your extra credit bonus points for attending this webinar. And of course, all the information for the prize can be found at www.herox.com/indeep. And now I will introduce my esteemed colleague and our Chief Engineer in Water Power, Joachim Weber. He comes to us with many decades of experience and expertise in wave energy and hydrodynamics, and formerly worked at WaveBob in the industry, and so brings a wealth of industry knowledge and experience to our community. Thank you very much, Joachim. Please take it away.
Thanks, Nicole, particularly for this flattering introduction. Okay, so good morning, good afternoon, everybody. Welcome to this 2.0 on innovation methods. So what I did the last time in the previous 2.0 webinar, I want to remind us on previous content. So you see the table of contents from the previous one on the left-hand side. I'm going to go through this a bit speedier than last time, and then we'll add some novel material. But I really believe that context is necessary. Jumping into the new content would be a little bit out of context and probably not so easily understood. So you see on the right-hand side that we have one other point where we then add to TRIS, the techniques for inventive problem solving in wave energy, where we add an example. And there we go. As Bill mentioned, please provide questions as we go along. We'll have a good bunch of time at the end, 20 to 25 minutes or something like that. Introduction context. First of all, in terms of context, I want to say 2 things. So the inventive methodology that we're discussing here similar to last time, is only one of many. However, it's the one that we have used mostly in our internal projects. It's also one that we promote and that we want to disseminate and support for use more widely, because we feel it's very impactful and very strong. It has one critical difference to many other innovation methods, that it goes deeper into the domain, into the task of ideation. Many innovation methods are good at expressing the problem and are good at assessing ideas, but don't go really deeply into the process of how do I actually come up with an idea. So that's why we've taken preference for this theme and this topic. And but we are happy to include a wider spectrum of methods in our last and third webinar, which we're running in the 3.0 series of these webinars. Another context in relation to the prize, to make this clear, there is no requirement of performance with respect to these methods in the prize. This is only a supportive webinar that may help you adapting your technology to requirements in wave energy. We'll see later on that there are quite a few contradictions that need to be resolved in the design of a wave energy converter. And since many of you may come from other domains, you might encounter such things when you want to apply your technology to serve as a DEC, a distributed embedded energy converter transducer, or a DEC-TEC metamaterial. So hopefully in that sense, it can also be useful. So these 2 points about context. Let's get going. Innovation process, and this is previous material. Yeah, I want to just emphasize here that following the problem statement, which I believe also is an opportunity statement, we have this process of ideation. And similar to the comments before, it sometimes happens that the problem statement isn't really fully understood, but ideation, as it may happen naturally, kicks off. And then sometimes the concepts and the ideas that are being found a little bit more look for the problem that they solve rather than the other way around. So in sequence from left to right, problem statement formulation, ideation, assessment of the ideas, plural, is important here, and then the development process that brings all this together. So in terms of problem statement, we want to find out and express what the system is supposed to do. These are functional requirements. These need to be solution agnostic, because I don't want to start with a problem statement that is already biased for a solution or has a solution embedded into it. And of course, these can be structured, these functional requirements, in hierarchies and in compatibility with GTR. Ideation. Yeah, we want to have the ideation driven by the problem statement in forms of functional requirements. We want to generate more than one idea. We want to have them compete against each other and iterate through them. In terms of assessment, if we want to iterate and want to have them compete, we need to understand how good they are. This is where we've developed for our purposes the TPL assessment, and you have separate webinars on that. So we want to identify strengths and weaknesses and make, and as consequences, we might prioritize certain concepts or we down select certain concepts in our own technology development process in general, again, not prize-wise. Then the development itself, of course, is a process in which we try to strive to improve the quality of a technology, but also to mature it. It's an iteration across different concepts. Okay, just that as a high level. Impact of different innovation categories. So there's a lot of innovation going on. We hear a lot of things about that ideas only are as good as many other things that need to be coming with the ideas. It's good to have a look at how impactful certain innovations are. And there's a few, the top 3 categories, which are not kind of earth-shattering. Sometimes it's kind of an application of sometimes it's no knowledge. Sometimes it's application of a solution in a different domain or in a different industry. But then at lower percentage of occurrence, we have different levels. Sometimes we find actually new technology and not transfer technology. And sometimes we even find new science, even though I want to correct that expression. It's just new that we understand the already existing science, of course. So let's go to TRIZ, this technique for inventive problem solving. A bit of background history. You may remember some of this. It was developed by a Russian patent engineer, and he went through a large number of patents. He was followed by others who went through even more patents. And he asked himself, hey, can I identify the valuable patents and maybe find a method that gives guidance on how these were found? So he went through a large number of patents, as mentioned previously, and identified the problems that were encountered in these patents and these innovations as contradictions, always solving a contradiction. And he asked himself and identified a finite set of recurring problem types and a finite set of recurring innovative principles. And the beautiful thing about that is when you then go through a lot of innovations and patents and you can match these, you can then say, okay, if I have a certain problem, I know from experience that a certain inventive principle, and with that, a certain way of thinking might be useful and has been useful before, but it's only kicking one in a certain thought direction. Okay, so what he found is he found a finite number of problems in what he refers to as root contradictions. And the contradictions are between two parameters and also a number of finite inventive problem-solving techniques. Okay, you might remember these graphs from last time. So what you then have, these of course, these problems categories are a little bit more general. So if you encounter your specific problem of the application you're looking at, you need to translate that into the more generalized problem or the typical problem, find a solution through TRIZ, or find a way of thinking within TRIZ, possibly find a solution and then translate that back to your special situation. On the right-hand side, it's the same thought process, just slightly differently presented. Okay, now how do we have access to these contradictions? The contradictions are expressed within two parameters. There's different ways on how this has been done. And if you can find the right case within TRIZ, it points you towards inventive principles. These are number coded, like you see in the box on the bottom right. And in this case, those numbers stand for those inventive principles. We'll go a little bit further into some examples of these. Some are, and of course, many of these principles are not novel. They are known principles. The trick about it is the allocation from problem to inventive principle. And there's lots of them. So the whole matrix of contradictions is this kind of size and points towards inventive principles. So there's a lot of work has gone into that. That's where you can see the reflection of these unbelievably large numbers of patents that support this. Okay, here are the inventive principles. Let's pick out something. Other way around, for example, 13 would mean to change the orientation or the sequence of something. Homogeneity, maybe making something homogeneous or making it heterogeneous, and there's many forms of heterogeneous. Looking in dynamics, yeah, many of these are very expressed very much in a design engineering world. However, they can be taken in a more abstract level and can be transferred to completely different physics, and it can be even transferred to organizational processes. Okay. Yeah, when we want to solve contradictions, we do not want to just make compromises. We want to truly dissolve them. We want to get rid of the constraint of a compromise. What is a compromise? A compromise is typically a combination or ideally the best combination of two criteria which are in a certain contradiction, and the one criterion doesn't allow the other criterion to be at its best. And you may know the term Pareto frontiers. So these are parameter lines that show the best result for parameter B given parameter A is a certain value. So this line of compromise You'll find these maybe even in multi-parametric situations when you do a multi-parametric system optimization and scan through the optimal settings with numbers of degrees of freedom within that. So we want to really break those to solve those. So we come into areas that are below this, where everything looks good. Of course, that's ideal, maybe ideal thinking, but why not? Ideality is also a principle of TRIZ to say, I don't start from what I have. I start from the ideal solution and reduce this ideation, this ideality with requirements of the reality and see where I come out there. All right. Benefits are, and many large companies have used this method. Years ago, Toyota made it a requirement that every engineer in the company needed to be an expert in this method. And there are many other examples. So the benefit of TRIZ is that it does two things. It can increase the quality of what's being understood in the problem statement because it's expressed differently, the quality of what comes out of it, and it strengthens where you see the arrows on the right, it strengthens the creation process of coming up with an idea. All right, so reasons to use it. It's systematic, it's audible, repeatable, it's based on proven successful patterns. So these successful patterns, of course, kind of try and embrace a lot of knowledge of innovative thinking. And yeah, I mentioned the ideality. So there's other methods and adjacent tools within the overarching theme of TRIZ, and some are mentioned down there. Okay, let's look at wave energy. In wave energy, technology development framework, as presented before, we tried to move around the map of innovation with respect to maturity, technology readiness levels, quality, how good is the technology performance levels, and move around this map. And it's very critical, as seen before in the TPL process. Apologies, my phone is telling me a certain time. Don't need that. Yeah, we want to move around effectively and efficiently in this technology development process. That means we need to expose what we have to assessment all the time, like mentioned in the innovation process, and we may need to resolve contradictions, improve what we have, or even come up with new things for systems or subsystems. Okay, and yeah, this is just expressed with these generic technology development trajectories, where they have been investigated with respect to their cost, time, and risk. And the red path is unfortunately the path that is often pursued, driving things to high technology readiness levels while delaying the improvement of a technology. And unfortunately, due to the high cost and time, and predominantly due to the very much higher risk of this path, it occurs quite often that technologies do not succeed to market entry. They may end up in a cost dilemma in high TRL, where fundamental conceptual improvements cannot be implemented because we're too mature to do this. The green one is much more efficient, faster, less costly, and particularly much less in terms of risk, which you see the kind of the orders of magnitude you see in the bottom line. Okay, now we've had very good success with applying this method. That's why we want to promote it and share it. And yeah, that's maybe the main thing I want to say here. One of the evidences of that it is impactful is that when we applied it to a certain archetype of wave energy and identified some of the downsides expressed as contradictions and applied the methodology, the innovation was so strong that it even jumped not just into a new version within the archetype, but even jumped into a different archetype. So from having a multiple body system, applying TRIZ, we came to oscillating water columns. Of course, they exist and have been around for ages in nature and in engineering, but it just shows the capability of the method to truly jump into a different domain of solutions. Okay, we can apply this to different levels of the farm, of the system. So this is farm level, unit level, subsystem, component, even also the operational process. And InDEEP, of course, at the different levels that the InDEEP Prize is concerned with. But I just want to mention again, it's not a requirement. It's maybe something you find useful in the process, in the progress of the prize. Now, with all this in mind, I want to show you an example, a prominent example in wave energy on how TRIZ can be applied usefully. And I apologize, my camera seems to have gone off. I'm here. Okay. All right, let's look at this example. So, and I want to make a connection to the general wave energy introduction webinar that we had, I believe, 2 weeks ago, and use some of the slides and bring them into this context. So we talked about forces on a floating body, individual body or multiple bodies, and we looked at the governing equations. So the governing equation I want to present here again in the most simple case is a normal oscillating system, 1 degree of freedom, inertia, damping, restoring terms driven by excitation terms on the right-hand side. So this is all clear. We identify that in its simplest form of modeling and understanding, this is mass spring damper system, as we often refer to. We know how these systems behave. Also a graph we had the last time. The more important thing is here that the system response, which is the highest line here, that graph, starts with following, just behaving as the excitation at low frequencies, and goes over to non-reacting at all at very high frequencies, and in the middle somewhere has a resonance. So we want to exploit this resonance because it's a strong response of the system, meaning we have the waves, we want the system to respond strongly to those waves, and we want to exploit the response of the system by extracting energy out of it. Now, these systems, of course, have natural frequencies that are driven by the inertia and by the restoring force. So by natural frequency. Sorry, I said resonance. I want to make it really clear that resonance and natural frequency are two different things. The natural frequency is the frequency of the freely oscillating undamped system. And typically very close to it, we have the resonance frequency, which is the frequency of the maximum response of the damped and excited system. And so they're slightly different due to the damping that's present. And if it wasn't damped, we would have an unrealistic result in terms of the amplitude. Okay, going back to this shape, knowing this now, what is important for the system response, we can look back at the shape and we can consider that the natural resonance, sorry, I should have the natural frequency here, is driven by the mass of this body on the right. It's driven by the stiffness to which it responds for displacement. And we are talking about heave here. So it's going up and down. The other degrees of freedom are not considered here. It's driven because of the mass by its volume. We've got buoyancy at play here. It's a freely floating body. And its shape, particularly with respect to the surface piercing area, because the surface piercing area of the body defines how strongly it resists and restores to vertical displacement. Okay, then in terms of the excited response, again, we have the mass, we have the stiffness, we have the volume. However, we also have an excitation of the system because it's now the excited response. And for this excitation, we have a very important influence of the shape of the system, but this time not so just the surface piercing area. This time it's the entire shape, because this entire shape is going to diffract the waves, and it is going to take the surface pressures out of this diffracted wave field and integrate them up to an excitation force, excitation moments as well. So what does that mean in order to get this response on the right-hand side and influence it? Unfortunately, for a simple floating body at certain sizes that are meaningful for techno-economic success for wave energy conversion, these resonance frequencies are unfortunately at too high frequency values. So the system would like to respond at a high frequency, but the waves are at a much lower frequency. So we need to make design decisions that brings the natural behavior of the heaving buoy into the region of the waves. And we just looked at kind of key design aspects in terms of mass and volume and shape. Okay, let's go on. So we have, unfortunately, a lot of contradictions if we want to achieve the influence of the natural frequency and the response. And this is quite a lot, and we can't go through all of them, but I want to emphasize a few. So we just seen simply from the formula, we have large mass and small stiffness is what we want for the resonance frequency. That doesn't come naturally together, because if I have a big body, I might have a big surface piercing area. That's emphasized here a bit more precisely. Then we have things like large volume versus small surface piercing area. The large volume is through the buoyancy connected to the volume. That'll bring for a low resonance frequency. And the surface area, piercing area, is linked to the stiffness, but also implies that maybe I need a small volume for that to get to a low resonance frequency again. Then we have things like large surface piercing area versus small surface piercing area. So for large surface area piercing area, I want a large excitation, so it's likely that I have a big surface, and for the resonance to be in the right place, I want to have low stiffness. And it goes on. So in terms of excitation, I want to be close to the waves, and I want to maybe have a flat surface that's particularly orthogonal to the upward orientation, because that's the degree of freedom I want to excite. And it should be large for getting as large excitation, to get a lot of energy provided into the system, to get a large response, to get a large output and energy output, energy absorption. At the same time, I want a small surface piercing area. So these are really in strong contradiction in terms of the shape we're looking for. And another aspect is also that for mentioned reasons, I want a large volume, but I also want for excitation, for example, and surface areas, but I also want a low mass, which is very important for an efficient and effective control of the system, which is a much more sophisticated aspect. But you can see there's, it doesn't come naturally to come up with the right shape for a heaving buoy. So what can we do? So let's take one of these contradictions, this one. Large mass versus small volume, which looks like a contradiction, and find an associated contradiction in TRIZ. Here's a zoom into a part of this huge matrix that I showed you before. It's a different version, but it's the same thing. And if we zoom further into it, we can find a category which has the characteristics of weight of a moving object, and on the other hand, volume of a moving object. Moving object because, okay, it seems important that we are experiencing inertia. And this TRIZ formulated contradiction points us towards 4 different inventive principles. Okay, let's look at those. The ones that are suggested. One is called nesting. That means maybe embedding a certain function or a certain design aspect into a different one. A replacement means, well, trying to achieve what I need by different means and achieve it better in that way. Maybe also partial replacement. Using gas and fluids, that might be useful for some cases. Composite structures, of course, are often a solution to different problems. The one we want to pick out here is replacement. So a symbol for this is simply change, key characteristics of one thing by some other things. But as I mentioned, there could equally on the right-hand side, there could be a square and a triangle, because I add the triangle and I've separated the function into 2 providers of this function. The formulation that's used here is, if a certain design aspect doesn't deliver the function I want to see, I may replace it or I may partially replace it. So now we go to a very prominent example. It's probably one of the leading companies at the moment. Just completed a few months of testing in Portugal, in Arcosaveira, and apparently with good results of a full-scale system. So that's core power. You've seen core power previously in the introduction to wave energy as a heaving point absorber. So it's exactly the system we looked at, and it also has all these challenges we looked at. So this here is just to introduce what the system looks like. So it's a heaving buoy. It can move in surge and other degrees of freedom, but it maintains really the active power absorbing degree of freedom is heave. It's bottom referencing, so it's working not against the different body, it's working against the seafloor. You can see some dimensions on the right-hand side. So that's the principle. Goes up and down, the relative motion between the hull and the internal mechanics is used. Okay, so the problems in terms of having the right system response, I think, are clearly described and understood. So with the separation of the restoring coefficient, that was one key aspect, while maintaining the volume, we have hydrostatics. This is exactly what we expressed before, the surface piercing area that gives a restoring force to bring the system back into its initial unexcited equilibrium. So the heave stiffness. So what has been implemented in the system is that another stiffness has been added to influence the overall stiffness of the system. And this stiffness or restoring force, because we want to reduce the overall stiffness from what we already have from hydrostatics, was introduced as a mechanical solution that provides a negative stiffness term. Now, what does that mean? A negative stiffness term means if I displace a system from its equilibrium by displacement x in a certain in this direction, it doesn't come back. The further I displace it in that direction, the further it's being pushed away. So it's force proportional to displacement, but not leading it back, leading it away. So if I add this kind of force to the hydrostatic restoring force, I get a superposition of both. And if this negative contribution is smaller than the positive contribution, I still have a positive total contribution of restoring. However, it is reduced than the original pure hydrostatics. Now, how is this implemented? Let's have a deeper look into this design. You can see that when the center body is moving or remains static in relation to the heaving buoy that goes up and down, we have these rods here, hydraulic rods that can be actuated with a spring component, and they are long when there's a large heave displacement, and they are short in the mean position. And if there's a positive pressure in them, they want to be extending. That means if you give them an opportunity to extend with a heave displacement, they will push further out. And another snapshot of the situation is on the right-hand side, where you see a different vertical displacement. Maybe it can be noticed by the free surface, the water surface level, and the position of the buoy. Here we have the buoy coming out of the water, free water surface level here. And now the orientation of those hydraulic rams is different. The heave displacement, the relative displacement is different internally seen as well. We can see the column length here and the commute length here. So we've added an internal mechanical force that acts like a restoring force. It's negative, it introduces instability. However, the positive restoring force from the hydrostatics are larger, and we get the stiffness to drive the dynamics of the system that we want. Okay, what does that look like? We have now a resonance that is moved into the right frequency of the waves. And here's an example where the system responds with an amplitude increase. So with a meter wave height, for example, or 1x wave height, the system can achieve 3x amplitude at the right frequency. Additionally, by influencing and controlling the forces on those rods, the system can be tuned. So the frequency of resonance can be brought up and down. Maybe there are situations when you actually don't want this strong interaction with the waves, particularly when they are getting too large. Okay. And another aspect that I want to bring in here, we could go the same chain of inventive principle of, seeing a contradiction, inventive principle, and what the solution is. From another aspect that's implemented here, again, the look at the buoy, what we see here, that we have a large displacement, there's a lot of volume, and maybe it's possible that the mass inside actually doesn't satisfy the volume displacement and doesn't satisfy buoyancy. And that's actually the case. So the mass in the buoy is significantly lower than the displaced volume in the equilibrium position. Now, how is that achieved? It would have to, lift up if that's the case. So what is being done is that the rod and the connection to the seafloor is provided with a pretension. So this pretension allows the system to sit deeper in the water than it normally would by buoyancy. What do I achieve with this? I get the surface areas that I want for excitation and radiation, essential for wave energy absorption. But I also get the reduced mass, which I want in order to have an agile, very responsive system for effective control. So this is a complete other path of thinking additionally that's also implemented here. And we could have displayed that in the same sequence of thinking as we did that with the other one. All right, that's it for today. The next TPL assessment, the next webinar that comes up is TPL assessment 2.0 next week. And the connection to here is we did a TPL assessment for core power, and for us, it was a valuable experience because we don't often assess technologies at its high technology readiness levels. And here's a testimonial from Patrick Möller, who's the CEO, who also saw the value in that. So with that teaser, I want to invite you to participate in the next webinar as well. So that's all from me, and open to questions. Hello?
Yep. Thanks, Joachim. I see and hear you. Yeah, I don't know in screen share if you can see the questions in the chat. I think.
Quick question here. My screen share, did my screen share drop at some point?
Not for me.
Okay, good. Yeah. All right. Yeah. Okay. Right. The chat. Let's see. So we're happy for you to speak up.
They might not be able, we need to get the admin to let them speak. I think the participants are muted and only the panelists, I think, can speak up.
Yep, if someone does want to verbally ask their question, they can raise their hand and I can give them the permission to unmute, so.
And maybe I'll take this opportunity, Joachim, while we're waiting for questions to come in, that we're doing these sessions, these workshops, supporting our prize goals that are in the rules document. What section 1.5 of the rules document talks about our goals. We're trying to leverage WEC innovation methods, build a solver community, encourage the development of novel WECs, and refine WEC innovation methods more generally. So we want you to thrive during the prize, but we're doing the prize because we're excited about, fundamentally interested and excited about this opportunity for these distributed embedded energy converters, how they can help us solve these challenging wave energy problems and all these contradictions as Joachim brought up. So that's really the motivation for these enrichment activities. We want to thrive in U.S. Green energy sector. I do see, Joachim, a question that just popped up. Do you have a recommended reference for TRIZ?
Yes, we can provide this. There's a lot of courses. We all ourselves did a course, which I can recommend. Yeah, let's say we'll provide some links on the HeroX website.
And to the person that asked the question, there's in the rules document at the end of it, I think it's Appendix 3. There's a big reference document section, and we do have references to. I wish I could do this on the fly. Or maybe it's Appendix C. Yeah, Appendix C is our reference document. So we've got all the training resources and reference material. So that's also your first stop to take a look at. So thank you.
Okay, good. I think the other things I answered. The whole dialogue that's here about tank testing, I think, is covered. If not, please speak up. And yeah, we've got an example for the TRIS book. Yep, that's a good one. Thanks, Blake. Any further questions? Or, of course, beyond what was mentioned at the setting, the context at the beginning, any wishes for what should be included in the next webinar?
Joachim, I see questions in the Q&A, not just in the chat. Did you all get to those? Sorry if I missed that. So
Oh,
do you
yeah,
have a preferred, do you have preferred materials for parts? How detailed do you want our graphs?
Okay, that's a general price question. My understanding is no, there's not a preference for materials. That's part of your solution. We just have requirements. How detailed? I would say they should be detailed enough to fully understand what's going on. If you provide more detail, that's nice, but it's not a must-have. We wouldn't want to be in a situation where we don't understand what you are trying to tell us. Blake is typing. Do you want to speak up, Blake, if that's quicker?
Sure, I'll just echo what Joachim was saying. So far as I know, there's no particular material type that we're interested in. And then in terms of how detailed the graphs, exactly as Joachim said, enough for us to understand. I would even take it a step further and leverage like the scientific method. There needs to be enough information such that we can replicate.
Okay, we've got another quarter of an hour.
Joachim, while we're waiting for any more questions, I just wanted to chime in about the leaderboard. If you have not already confirmed your eligibility for phase 2 for leaderboard points, we'll need you to do that to earn leaderboard points. And if you did that during phase 1, you also need to repeat that. The phase 1 leaderboard entry does not carry over. So it's brand new in phase 2 for everyone to enter into the leaderboard. Thanks.
Okay, it looks like we have no more questions in the Q&A.
I think one just came up, Joachim. Need to be physical test either, can be simulation, question mark. Do you want to, could we give, or yeah, maybe, do we want to let Guillermo speak to that or unmute him, or can you just answer that right there, Joachim?
Yeah, in terms of the different phases, you know that phase 1 just required a description of your proposal. In stage 2, we want to see the deck in a real world situation, so in a test bench. And yeah, and the same thing at phase 3. Maybe we can speak about that more detailed, looking at the rules, but yeah, a simulation might support your input. Surely that's valuable, but I don't think it'll replace the physical demonstration.
Yeah, I'll chime in here and again, really support what Joachim was saying, is that a key aspect of the prize is those empirical showcasing of your ideas. So in as much as numerical or simulated results can be used to support your ideas, as Joachim said, we want to see something in the real world.
So Guillermo, definitely take a look at the rules document section on that. And if you have any questions, put that in the forum on the Hero X page. You can ask your questions in the forum and we'll get back to everybody. But if it's, so take a look what's in rules document. If it's clear, great. If it's not, ask the question. We will get back to you. We'll get back to everyone. And maybe I'll just plug the forum more generally on the InDEEP Hero X page. There's a section called the forum. So if you've got general questions, please post them there and we'll get back promptly and you'll get a response. So we want to have good two-way communication, be responsive, and really hear where your challenges, your concerns, your interests lie. And because we really want to help this community, the solvers working on this prize.
Okay, maybe we'll close it here.
All right, well, thanks everyone for attending today. We very much appreciate your new interest, your continued interest in the InDEEP Prize. We were very excited to see the results of phase 1, all the different methods and techniques. And we're even more excited to see what you can do in phase 2. So please read your rules document. Please engage on the forum. Thanks for attending these workshops. We're trying to build the community, help you guys thrive during the prize, but also post-prize. And we look forward to seeing you at the next webinar. Thanks very much, everyone. Have a good day.
Thanks a lot. See you again soon. And follow up with further questions as they occur.